All right, so we've seen a lot of different details on how trees are generally working and how graphs are generally working. Let's take a look at the implementation of a binary search tree to better understand how this is generally going to be coded. And generally, the main idea is going to start pretty similar to some of our other data structures. We're going to be using a node, as we'll call it, to represent the data inside of our tree. And generally, this node is going to have three different attributes for it. The first one is going to be a value, and we'll pass each of these into the actual initializer itself. The second property is going to be the left child, and the third property is going to be the right child. So as I mentioned before, inside of a binary search tree, your nodes are each going to have either 0, 1, or 2 children, and the children will either sit on the left-hand side, meaning that they're smaller than the value that we're currently at, or on the right-hand side, which means that they're bigger than the value that we're currently at. So this is how we're going to keep track of that information. Now, the actual binary search tree itself only needs to keep track of really one piece of information, and the one piece of information it needs to keep track of is the root. Because our graph is connected, we can get from one node to any other node inside of the tree. So we generally only keep track of the root node, which is then going to be connected to everything else in the tree, since we'll be able to get to everywhere from the actual root itself. So this is all we really need to do. So then the next natural question is, well, how do we do things with the actual tree itself? And we'll start here is we'll start by talking about the inserts into the tree. To insert a value into the tree, basically the main idea of what we're going to do is we're going to start at the root, and we're going to check if the value that we're trying to insert is less than or bigger than the root. We're then going to move to the left or right based on the result of that. So we'll move to the left if it's smaller than the root, move to the right if it's bigger than the root. We'll then end up at another node, potentially. And at that other node, we'll do the exact same thing. We'll say, well, do we need to go to the left or right of it? And we'll keep doing this until we reach an empty spot. And that empty spot will be where our node will be placed. Now, as I'm discussing it, there's a bit of an interesting problem with this style of insertion. The main problem is that on each time that we pick either the left or the right, we need to update the node that we're picking in order to tell it that we're placing a node somewhere to the left of it, right? So we have to kind of update each of the different nodes as we're iterating through. The easiest way to do this is actually using recursion. So you'll see recursion is going to be a very common theme for our binary search tree operations. We're essentially going to be applying recursion to be able to iterate through our trees, to be able to reach the points where we need to reach in order to do various different operations. Now, I will note that in a lot of the cases, we can also do this without recursion. I always show the recursive methods because they are the most common methods, they're the cleanest methods, and generally, if you see an implementation of a BST, it's probably going to be recursive, so they're the ones that I generally show. But I will just note that usually you can find non-recursive methods for these as well, but they're fairly messy, so just be warned that there's a trade-off between recursion and non-recursion. So let's talk about our insert. The way that I generally set up my inserts is going to be like this. I have a main function called insert, and then I have a second function called insert aux, or an auxiliary function. The idea of the auxiliary function is that it's the one that we can use to actually do our recursive calls. The reason that I generally set things up like this is because we need to update the root of the tree with the results of the actual insertion. So it's easiest if we could just do something like this. Self.root equals self.insert aux, and then we pass in the root as our starting point and the value that we're trying to insert. At this point, this function here, the insert aux, handles all of the iteration, it does all of the updates, and then it just returns back the new root node for us to be able to use. So that's the general purpose of these two different functions. The idea of the insert auxiliary is it's going to start by checking to see if the current node that's been passed in is none. If that node is none, then we're just going to return a node with the value that we are trying to insert, and it will have no left or right child. This is essentially the end case for this, right? So basically, once we reach a node that's none, we found a space to insert our current node, so we go ahead and return that back as our result. The next check that we'll have is to see if the current node dot value, so if there is a node and it has a value, then we want to see if it's less than or equal to our current value. If it's less than or equal to our current value, then what I say is we're going to update the right of that node to be equal to the result of doing a recursive call with the current node dot right and the value that we're trying to insert. So basically what we're saying here is if the value we're trying to insert is smaller than our current value, what that basically means is that the right-hand side, we're going to start iterating. So we're going to update the right-hand side to be the next iteration that we actually complete. So that's the general idea of what we're happening here. And then finally, the final case here is really if it's going to be greater than the value, right? In this case, we would move to the left-hand side. So we do basically the exact same thing, just with the left-hand side. And we'll do this with dot left and value. And that's really all there is to it. All we do at the end of here is we just return back the current node. So you'll actually see that this is like a pretty straightforward structure, right? The recursion here is pretty clean. It's just a few lines of code that we need to do to actually get this to get up and running, right? So it's a fairly straightforward process to actually do all of these different updates here. And as you start working with trees more and more, you'll start to notice the patterns of how we iterate through the trees and how we actually, update and change values. So you'll start to get really clear on how we do these different iterations with the recursion. A few final pieces here. The first is that we want to test this to make sure that it actually works. And that sort of process is a little bit more tricky, right? So because we don't have any way of printing out the tree currently, it's a bit hard to actually test it. But basically all I'm just going to do here is I'm just going to do a few inserts and just make sure that, it doesn't give me any sort of like errors or anything like that. And I'll actually show you that we could probably do a little bit better and see a bit of information about the tree. So let me go ahead and just print this out. So we'll just do this first test here. Oops, node.py. You'll see that we get no outputs, which means that we didn't get any errors, which is great. What we could do here is we could actually print out b.root.left.value, and we could take a look at what that ends up being. You see that that ends up being 30. So basically 50 ends up being the root because it's the first thing that we insert. The thing to the left of it is 30 because it's less than 50, right? So that makes sense for where we inserted that. And we can also take a look at right.value and just make sure that that's 70, which indeed it is, right? So this seems pretty reasonable as, a method to actually get this up and running. So if I were to insert 40, for instance, it would be to the left of 50 and then to the right of 30. So if I do, dot left, dot right, dot value, that should take me to 40, right? Now this is very convoluted, right? I'll show you a lot of different ways that we can iterate our trees in later videos. I just want to do this as a quick check just to make sure that things are inserting in the right places, and it looks like they are. So that is great so far. Final piece before we move on to other methods is going to be time complexity, right? So what is the time complexity of our insert? As I was telling you when we were taking a look at that binary search tree is that we remove effectively half of the tree every time that we iterate, right? Anytime that I pick left or right, I'm basically removing half of the tree from consideration. So generally, we should get an O log of n time complexity since we half the size of what we're searching every single time. Now, I will note that there are circumstances where this can actually be worse. A circumstance where this could be worse is consider if I had a tree that had a root, right? And that root only had things bigger than it, meaning that the right was the only thing that was updated for each of the nodes. In that case, you would actually get a sequence that looks like this, and it looks a lot like our linked list. And for that matter, it basically is our linked list since only one side of the tree is being updated. In this situation, we would actually have something closer to O of n as a time complexity for our insertion since it just goes all the way to the right and inserts, right? This sort of thing is referred to as the tree's balance. A balanced tree is going to be a tree that has a specific height to it, and we didn't really talk too much about height. Height is basically the longest path that exists from the root to any of the nodes without children on the tree. We call those leaf nodes. So from the root to the leaf, it's the longest distance between them. And if a tree is balanced, what that would mean is that the height of the tree is equal to generally log of n. You'll often see people say that it's equal to O log of n, right? But generally I would say it's about log of n as the height itself. If the height is log of n, it means that the tree is balanced. So there's basically about an equal number of things on the left and right hand side of the tree itself. If we have that situation, then our insert would be log of n. If we don't have that situation, it may perform a little bit worse. So then one of the things that's going to come up here is there a way to make sure that our height is always going to be equal to log of n? And there is. And we're going to talk about that actually in the next section where we talk about red-black trees, which are a special variation of a binary search tree that maintains this height property of log of n. For now, I'm just going to say to you, this insertion is log of n. We're just going to assume that it is. And basically, in a future video, we're going to create something that actually makes sure that this insert always operates of O log n. So with that, you now have the basic idea of how the inserts are generally working for our binary search tree. So now we can get data into our binary search tree. In the next video, we'll talk a bit about actually retrieving data from our binary search tree. Then we'll talk about other fun things like deletions as well as iterations through the tree itself. So thanks so much for watching this video, and I'll see you in the next one.